Good morning. The following session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right. So after going through quite a few questions from section 9.2, which we'll do here shortly, we're going to go on to section 9.3. Okay, so the first question we're going to look at, this is from Webassign. This is section 9.2, problem number 30. And actually, the answer that the student has isn't wrong, it just isn't finished yet. And we're going to take a look at that. So let's see here. Okay, let's take that back to the other screen. Now, this may seem like a crazy way to go, but until you get comfortable with it, it's probably the best way to go. What I'm going to do, I'm going to change this expression into exponential notation, which would make it x squared y squared to the 1/8 power. The index is 8, therefore the denominator of the exponent is 8. Then I'm going to simplify that. So this becomes x squared to the 1/8, y squared to the 1/8, which becomes x to the 1/4, y to the 1/4. Then I'm going to change this back into radical notation, which is the 4th root of x times the 4th root of y. That's what the student had, but you can go one step further, and that is you can combine them under the same radical. So this is the answer that they were looking for. All righty. And with that, I'm going to go to another student's work. Let's see here. We want 47E. And here we're going to look at, let's see, 2. And starting with problem number 21. Okay. Alrighty. So now we're looking, this is all of this is in 9.2. Problem number 21. It says change the exponential expression to a radical. Okay, and it looks to me like the student used a calculator to approximate the 5th root of 7, and they aren't asking you to do that. They just want you to change its form. Okay, so we've got 7a cubed b cubed all to the 1/5 power. Okay, so this would become the 5th root of 7a cubed b cubed. So we're changing the exponent to the index. And that's all they want you to do on that problem. Any questions there? Okay. We're going to go on to problem 23 in that same set of problems. And it has the following. A negative sign in front of 81, c to the 4th power, all to the -3/2 power. It says simplify the expression. And it says the variable represents a positive real number. Okay, again, I'm looking at the student's work. It looks like they used a calculator to approximate something. Also, the answer should have only positive exponents. All right, so let's see what we've got here. this is going to be equal to negative, okay, 81 to the negative 3/2 power, c to the 4th to the negative 3/2 power. Okay? Now, this is equal to negative 1 over 81 to the positive 3/2 power times 1 over c to the 4th to the positive 3/2 power. So by doing that, I got rid of the negative exponents. Okay. This is equal to negative 1 over, let's just take this piece right here, 81 to the 3/2 power. So we're going to do two things to it. We're going to take the square root, and then we're going to cube it, the square root and then cube it. What is the square root of 81? That's 9. And then 9 cubed, let's see, what is 9 cubed? That's 729. Okay, so this becomes 729. So far, so good? Now, going on, dealing with this piece of the problem, we have a power raised to a power. So we're going to multiply the exponents. 4 times 3/2 would be 6. So this becomes 1 over c to the 6th power. But we can combine these, and our final answer is going to be negative 1 over 729 c to the 6th power. Any questions on that before we go on? Okay, we're going to take a look at problem number 24, which says, simplify the expression. We have a negative, and then 8x cubed over 27, and that whole thing to the negative 1/3 power. Okay. Again, it looks like the student used their calculator to approximate something, and they're not asking you to approximate anything. They just want you to simplify the expression. Okay. So this is equal to negative 27 over 8x cubed all to the positive 1/3 power. So by taking the reciprocal, it changes the sign of the exponent. Okay? Any questions about that rule? All right. I'm going to take this negative sign and I'm going to attach it to just the numerator. So now what I've got is I've got negative 27 to the 1/3 power over 8x cubed to the 1/3 power. Negative 27 to the 1/3 power is negative 3. 8x cubed to the 1/3 power would be 8 to the 1/3 power, x cubed to the 1/3 power. So now my numerator is still negative 3. The cube root of 8 is 2, and the cube root of x cubed is x. Now, the directions say the variable represents a positive real number. And even if it didn't say that, we wouldn't need absolute value bars because we're taking an odd root, cube root. So we'd be okay either way. All right, any further questions on that one? That takes us to number 33, which says, simplify the expression 81 to the negative 5/4 power. So this would be 1 over 81 to the positive 5/4 power, which would be 1 over, let's take this piece and take a look at that. 81 to the 5/4 power, we could take the 4th root and then raise it to the 5th power. Well, the 4th root of 81 is 3, because 3 times 3 times 3 times 3 is 81. So we get 3 to the 5th power. And let's see what that is. 3 to the 5th power is 243. So our final answer is 1 over 243. Questions there? Okay. We're going to go on to problem number 35. It says simplify the expression. The variable represents a positive real number. So we've got 36 a to the 4th to the negative 1/2 power. So we could get rid of the negative exponent by making this 1 over 36 a to the 4th, that whole thing to the 1/2 power, which becomes 1 over 36 to the 1/2 power a to the 4th to the 1/2 power. Again, a product raised to a power, we can attach the power to each factor inside. Well, the 36 to the 1/2 power, which is the square root of 36, is 6. A to the 4th to the 1/2 power would be a squared. So there is our final answer. And finally, number 40. Are we good to go on? If I'm going too fast, let me know. We okay? All right, I guess we are. This is number 40. It says, simplify the expression. The variable represents a positive real number. We've got the 9th root of 27, x to the 6th. Okay. Well, let's see. That's the same thing as 27 to the 1/9, x to the 6th to the 1/9. This one is a little bit tricky. I can take 27 and I can write that as 3 cubed. Okay, 27 is 3 cubed. So 27 to the 1/9 power becomes 3 cubed to the 1/9 power. Now, a power raised to a power, you multiply the exponents. So this becomes 3 to the 3/9, which is 3 to the 1/3. This becomes x to the 6/9, which is x to the 2/3. But they want the answer, they want it in radical notation, okay? It doesn't say that, but it doesn't say to change it to exponential. So consider this, and again, this might be a little bit tricky. This is 3 to the 1/3 x squared to the 1/3. Why would I want to write it that way? So now I can make it a cube root of 3x squared. So that way I'm able to put everything under the same radical with the same index. Again, that one is a bit tricky. Okay, how are we doing for time? We're doing fine. Okay, I'm going to go to another person's work. And let's see here. Oops. That's not the one I wanted. 27. Here we go. Here's that. And 9.2 again. Okay, starting with 26. Again, if I do the same problem, because I'm doing some of the same numbers, but if it's the exact same problem, please let me know, okay? Because I may not catch that. So here we're going to look at problem number 26. This is still 9.2. It says, simplify the expression, write the answer without using negative exponents. The variable represents a positive real number. That whole thing about without using negative exponents, typically we want to do that. There are some cases where it'll have us leave a negative exponent like scientific notation, but generally speaking, your final answer shouldn't have any negative exponents involved. All right, let's see here. I wrote 20 and I meant 26. Okay, simplify the expression. It says b to the 5/8 power times b to the 3/8 power, the whole thing to the 12th power. Well, if we take a look inside, we're multiplying two powers with the same base. When you do that, you add the exponents. So b to the 5/8 times b to the 3/8 is b to the 5/8 plus 3/8, which is b to the 1, which is just b. So what we end up with is a b inside to the 12th power outside, or just b to the 12th power is our final answer. Okay, any questions about that? Let's take a look at number, let's see, 27. Simplify the expression. We have 7 to the 5/6 power times, yes, let's see if we can erase that, times 7 to the 1/3 power over 7 to the 1/2 power. All right, looking at the numerator, we're multiplying two powers with the same base, so we want to add the exponents. Okay, so we need 7 to this power. Well, we need to add 5/6 plus 1/3. So we need a common denominator, which is 6. So 5/6 stays 5/6. 1/3 we multiply by 2/2 and we get 2/6. So now we've got 5/6 plus 2/6, which is 7/6. Okay, so the numerator becomes 7 to the 7/6 power. Now let's bring the denominator over. When we're dividing two powers with the same base, we subtract the exponents. So this becomes 7 to the 7/6 minus 1/2 power. Well, 7/6 minus 1/2 is 7/6 minus, and again, we're going to multiply here by 3/3 minus 3/6, which is 4/6, which reduces down to 2/3. So there is our final answer. Again, those rules, properties of exponents back in chapter 5, you've got to know those well to be able to do this. All right. We good to go on? If not, you'll stop me, I hope.
I was wondering, would you be able to go back to the 14th slide just for a second? I missed one thing.
Okay.
Okay, thank you.
You are most welcome. All right. 28, perform the multiplications. We've got y to the 1/3 times y to the -3rd plus y to the 2/3. It says the variable represents a positive real number. Simplify your answer completely, so we don't need to worry about absolute value bars. Okay, so I'm going to distribute. I'm going to get y to the 1/3 times y to the -1/3 plus y to the 1/3 times y to the 2/3. Okay, now multiplying two powers with the same base, you add the exponent. So this is y to the 1/3 plus -1/3, which is y to the 0, which is just plain old number 1. Not 1y, but the number 1. Okay. Here, same thing. We're going to add the exponents. 1/3 plus 2/3 would be y to the 3/3, which is y to the 1, which is y. So our final answer is 1 plus y, or we could write y plus 1. Questions there? All right, here comes number 29. It says use radical exponents to simplify use rational exponents to simplify the radical. So we've got the 14th root of 5 to the 7th, which is 5 to the 7th to the 1/14th power, which is 5 to the 7/14 power, which is 5 to the 1/2 power, which is the square root of 5. As I say later on, when we learn some more rules, we'll maybe get comfortable with the idea of just going straight there. But for now, I'm doing it the long way. We good to go? All right. Number 30, use rational exponents to simplify the radical. So basically the same thing. The 16th root of x squared y squared becomes x squared y squared to the 1/16th, to the 1/16th power, which is x squared to the 1/16th, y squared to the 1/16th, which is x to the 1/8th, y to the 1/8th, which is the 8th root of x, y. Very similar to the very first problem I did this morning, different numbers, but same idea. And finally, for this set of problems, number 31, simplify the expression -64x cubed to the 1/3 power. Now, recall, you can't take an even root of a negative number, but you can take an odd root of a negative number. So this would be -64 to the 1/3 power, x cubed to the 1/3 power. Well, the cube root of -64 is -4. The cube root of x cubed is x. So there's our final answer there. Okay. And let's see, we've got one more student's questions, and I think we've still got some time. Let's see. I don't know if I'm going to get through all of these because I want to have lots of time left here. Let's see. Okay. I'm just going to do the ones that don't have the correct answer for this person, and then they can contact me later if they're still not sure about it. Okay. This is number 27, and the original problem was 6 to the 7/10, 6 to the 1/5 over 6 to the 1/2. I'm going to kind of jump to the finish line. This particular student had this answer, okay? I'm not going to go through the details, but the only thing that's not really finished with that is that you can reduce the 4/10. So this is the answer they had. This is the correct answer. Okay. Let's see here. Number 34, it says c to the 3/5 power times c to the 3/5 power over c to the 1/5 power. Simplify the expression. All right. And let's see. Multiplying two powers with the same base, which is what's happening on top, we'd add the exponents. So this would be c to the 3/5 plus 3/5, which is 6/5. Dividing two powers with the same base, we would subtract the bottom exponent from the top. So this would be c to the 6/5 minus 1/5, which is c to the 5/5, which is c to the 1, which is just plain old c. Okay. Let's take a look at number 37. T to the 6/5, t to the 9/5, plus t to the negative 6/5. Simplify the expression, the variable represents a positive real number. So we're going to distribute t to the 6/5 times t to the 9/5 plus t to the 6/5 times t to the negative 6/5. Well, here, multiplying two powers with the same base, we'd add the exponents. Washed my tongue, can't do a thing with it. So this would be t to the 15/3, which is t to the 5th. Okay. This would be t to the 0, which is 1. So our final answer is t to the 5th. Oh, wait a second. I made a mistake. I wrote the wrong denominator there. This should be t to the 15/5, so t cubed. My bad. Sorry about that. Okay, let's see here. We're going to look at two more, and then we're going to go on. Number 40, simplify the 9th root of 125x to the 6th. So this becomes 125x to the 6th all to the 1/9 power, which becomes 125 to the 1/9 power times x to the 6th to the 1/9 power. This is similar to a problem we did earlier. I can take 125 and write it as 5 cubed. Okay. So then I get 5 to the 3/9 x to the 6/9, which is 5 to the 1/3 x to the 2/3. And I could write that as 5 to the 1/3 x squared to the 1/3. And why did I put it together and pull it back apart? Because I wanted to have this common fraction exponent so that I could use that as my index. Okay. One more, and then we're going on. Negative x to the 4th to the 1/4 power. It says simplify the expression if possible. Assume that the variable can be any real number and use absolute value symbols when necessary. If the solution is not real, enter not real. Well, consider this. If x is positive or negative, whichever one it is, by raising it to a 4th power, x to the 4th would be positive or 0, but it could not be negative. So then the negative sign in front of it tells us that this base is negative, but we're taking an even root of a negative number, and that is not real. And there you have it, folks. So if I didn't answer all of your questions that you asked for, please email me or come to my office hour this afternoon. But I think I got through most of them. All right. So now we're going to take a look at section 9.3. There are two important rules in section 9.3, and you should, in fact, already know them, but not necessarily in radical notation. You should know them in exponential notation. Let me explain. Let's say we have a product to a power. All right, so like AB to the nth power. In this case, we attach the outside exponent to each factor inside. So AB to the n becomes A to the n times B to the n. For example, xy, the quantity cubed, is x cubed, y cubed. All right, now, if this rule is true, which it is, what if we had this? AB to the 1/n power. That would be A to the 1/n times B to the 1/n, using the same idea. A product raised to a power, you attach that outside power to each of the factors inside. Any questions so far? All right, let's take this expression and let's convert it into radical notation. That would be AB Oh, but we're going to take the nth root of AB, which equals the nth root of A times the nth root of B. So what that means is if we have a product inside of a radical, so if the radicand is a product, we can pull it apart and use separate factors of this product under separate radicals that are being multiplied together. Okay, so for instance, let's say I've got the cube root of 27x cubed. That's equal to the cube root of 27 times the cube root of x cubed, which would be 3x. Now, we actually already used this rule in the previous section somewhat. We just didn't formally talk about it. I just kind of said, well, what's this? What's this? Okay, but now we're formally saying, yes, that's legal here in the state of Mayo. Second rule, if we have, let's see here, a quotient raised to a power, we attach the outside exponent to the numerator as well as the denominator. For instance, if we have 2 over x, the quantity cubed, that would be 2 cubed over x cubed, or 8 over x cubed. Suppose we had a over b to the 1 over n power. That would be a to the 1 over n divided by b to the 1 over n. Converting that into radical notation, that's like having the cube root of, let's see here, 8 over x to the 6th, which would be the cube root of 8 over the cube root of x to the 6th, which would then simplify to 2 over x squared. The point is, if I have a quotient under a radical, I can split it up into separate radicals, the numerator divided by the denominator, but again, the index is the same in each case as it was in the original. All right, so we've got those two new rules. Now we're going to apply them. Before we do though, again, any questions? All right, here we go. Let's see. Now, we're going to do something called simplifying a radical. And I have the square root of 28. Simplifying a radical, the name may not make sense because the answer might look more complicated than the original problem. So think in terms of when it says simplify a radical, what that means is we want to take everything that we possibly legally can out from underneath the radical, okay? Now, the index is the key to this whole thing. The index in this case is a 2, an implied 2. We can take the square root of a square. So what we want to do is we want to break apart 28 so that it's a square, if there are any, times whatever's left over. So 28 could be written as 4 times 7. Now, I could have said 28 is 2 times 14, but that doesn't serve my purpose. My point is I want to get factors that are squares, because now I can break this apart into the square root of 4 times the square root of 7. But the square root of 4 is plain old 2. So I've got 2 times the square root of 7, or 2 square roots of 7. So I have simplified the square root of 28 by taking the factor of a 4 and unsquaring it, kicking the 2 outside. So again, the answer looks more complicated than the original statement. So it's like, how is that making it simpler? But there's less under the radical, and that's considered simplifying it. Okay, any questions on this example? Let's take a look at another example. 9 square roots of 54. All right, so my index is a 2. I want to take 54 and break it down into squares and leftovers. Well, let's see. 54 is what? 9 times 6? Oh, 9 is a square and 6 is 2 times 3. There's no squares in there. So I'm going to write this as that. Okay, 54 is 9 times 6, still inside the radical. And that's equal to 9 times the square root of 9 times the square root of 6. Now, 6 can be broken down to 2 times 3, but neither 2 or 3 or 6 are a square. So that's going to be stuck inside. So now I've got 9 times 3 times the square root of 6, or 27 square roots of 6. So I've taken this expression and simplified it, kicked out as much as I can outside of the radical. Questions on that example? Okay. Here we have the square root of 50x squared. It says, simplify each radical expression. All variables represent positive real numbers. So in this case, we don't need to worry about absolute value bars. Okay, now 50 is 2 times 25, right? 25 is a square. So I could write this as 2 times 25, and x squared is also a square. Then I could split it apart and write the square root of 2 times the square root of 25 times the square root of x squared. That's not going anywhere. That's a 5. That's an x. So I get 5x square roots of 2. Notice my final answer, I put the outside stuff in front of the radical. Okay. Now, this is a lot of writing. I'm going to do this problem again, but I'm going to skip a step to show you that, yeah, you could do it this way and accomplish the same thing. All right, so if I've got this, I could write that as that, right? So that's the same thing I did before. Rather than taking that next step and writing them all separately, I'm just going to do this. I'm going to say, well, the square root of 25 is a 5 outside. The square root of x squared is an x outside, and the square root of 2 is stuck inside forever. So a little bit less writing. Everybody okay with that? I'll take that as a yes. All right. Now, how about this? 4 times the cube root of negative 81a cubed. Suddenly, the index has changed. It's no longer a 2, it's a 3. So now we want to uncube cubes inside. Well, let's see. Negative 81 is like negative 1 times 9 times 9, negative 1 times 3 times 3 times 3 times 3, negative 1 times 3 to the 4th. Okay, and then I'm going to bring out that. So I could take this and break it down like that, right? But my index is a 3. So in fact, I'm going to write it like this, so that I have cubes and leftovers. Oh, negative 1 is the same as negative 1 cubed, isn't it? The cube root of negative 1 would still be negative 1. So here's what I'm going to do. I'm going to write it like this. Negative 1 times 3 cubed times 3 times a cubed. What I'm doing, I'm breaking apart the radicand into cube factors and leftovers. This is a cube, this is a cube, this is a cube. That's going to be leftovers. All right. So I've got the 4 that's outside already. What's the cube root of negative 1? That's negative 1. What's the cube root of 3 cubed? That's 3. What's the cube root of a cubed? That's a. What's left inside? The cube root of 3. So I'm going to multiply that all together, negative 12a times the cube root of 3. So I've got cubes and leftovers. I'm going to uncube the cubes, kick them outside, and then the leftovers are inside. All right with that. Okay. Another example, the 5th root of 64x to the 10th, y to the 5th. 64 is 8 times 8 is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th power. Okay. Now, I could rewrite this whole thing as 2 to the 5th power times, oops, times 2. Why did I take this and split it up? Because I'm looking for 5th powers and leftovers, okay? And I could take x to the 10th and write it as x to the 5th times x to the 5th, and then y to the 5th. So I've got 5th powers and leftovers. Do you see what I'm doing? I'm getting all the exponents to match the index. The nth root of a to the n equals a if a is greater than or equal to 0. There's a third big rule. What am I saying? If the index matches the exponent and the base is not negative, this cancels out, so to speak, or reduces out. Think about this. If you took this and wrote it in exponential form, wouldn't it look like that, which would be that, which would be that? Okay, here we go. Oops. What's the 5th root of 2 to the 5th? That's a 2 on the outside. What's the 5th root of x to the 5th? That's an x on the outside. What's the 5th root of x to the 5th? That's an x on the outside. What's the 5th root of y to the 5th? That's a y on the outside. Okay. Now, need some more room there. What do we have left over? The 5th root of 2. So I've got 2x squared y, 5th roots of 2. Let's go back for a minute and let's take a look at this. I broke that down into x to the 5th times x to the 5th, right? It's because I was trying to match my index. But if this exponent, not only if it matches the index, but if it's a multiple of it, x to the 10th, what's the 5th root of x to the 10th? Well, what's 10 divided by 5? 2. What's the 5th root of x to the 15th? That's 15 divided by 5, x cubed. So really, I want my inside stuff to be either matching the index or matching multiples of the index. So I could have saved a little bit of time there with that. In fact, let's look at another example of that to pull that out. So the 4th root of 32, x to the 12th, y to the 4th. 32 is 4 times 8, which is 2 times 2 times 2 times 2 times 2, is 2 to the 5th, which is 2 to the 4th times 2. Again, why did I take it and pull it apart? Because I want powers of 4 and leftovers, or powers of multiples in 4. 12 is a multiple of 4, right? So I'm going to write this as 2 to the 4th times 2 times x 12th times y to the 4th. What's the 4th root of 2 to the 4th? 2 on the outside. This isn't going anywhere. What's the 4th root of x to the 12th? That would be x to the what?
3rd power.
3rd power. Excellent. And the 4th root of y to the 4th would be y. And I've got the 4th root of 2 left over inside. Are you picking up on what I'm putting down there? Hopefully.
Trying.
Trying? Okay. I know it's a lot to swallow. Hopefully you won't gag on it. All right, now, let's say I've got a fraction under a radical. Recall that I can pull it apart. And in fact, I could do that. Because the square root of 4 is 2. Any questions there? All right. How about this one? I could write that as the square root of b to the 4th over the square root of 64 a to the 8th. What's the square root of b to the 4th? That would be b squared. What's the square root of 64 a to the 8th? Well, the square root of 64 is 8, and the square root of a to the 8th is a to the 4th. Final answer. So I can take a fraction under a radical and separate it into a numerator radical and a denominator radical if I want to. I can also go the other direction. I can take a fraction that has a radical in the numerator and a radical in the denominator, and as long as the index is the same, I can put them together in a single radical. So what we're doing there is we're going all the way back. Let's see here. Trying to find here. Instead of going this direction, we're going that direction. Okay, maybe that wasn't that helpful. So now, what is 128 divided by 2? 64. So now I have 64 under the radical, which gives me an 8. That's a lot nicer than trying to simplify this and then deal with it. So you can take that and put it together. You can take that and pull it apart. Okay. Now, last thing. It says simplify by combining like radicals. First of all, what's 11x plus 2x?
13x.
Okay. What's 11 square roots of 3 plus 2 square roots of 3?
13 square roots of 3.
And there you have it. Okay. We're combining like radicals. All right. Now, what's 30 times the cube root of 6 minus 10 times the cube root of 6?
Twenty cube roots of 6.
Yep, well said. All right. Now, suppose we've got 9 plus the square root of 45 plus the square root of 20 plus 16. The 9 and the 16 are already like terms, right? So we could combine those and make those into 25. The square root of 45 and the square root of 20, they don't look at all alike. However, we're going to go through and we're going to simplify each radical as much as possible and then see what we can do. Okay, so I'm just going to bring the 9 down and the 16 down. Okay, let's take a look at that. 45 is 9 times 5, right? So that would be that, which would be 3 square roots of 5. So the square root of 45 could be written as 3 square roots of 5 using the stuff we've been looking at. All right, let's take a look at this. The square root of 20 would be the square root of 4 times 5, which would be 2 square roots of 5. So now, having simplified the square root of 45 and simplified the square root of 20, can you see that they are alike? So I've got 16 plus 9 is 25 plus 5 square roots of 5. So simplifying each radical and then seeing if you can combine them. Now, I need to warn you, they don't always give you radicals that'll all simplify, or excuse me, that will be combined. In other words, you might have a situation where you've got several radicals and you simplify them all and some of them go together and some of them don't. So don't just necessarily assume that, oh, when I get done, they're going to go together. But you do want to simplify each radical as much as possible. Kick everything outside that you possibly can. Okay, I'm going to do one more example before I set you free out into the world. The square root of 20 plus the square root of 125 minus the square root of 80. Okay, well, the square root of 20 would be the square root of 4 times 5, which is 2 square roots of 5. Okay. The square root of 125 is the square root of 25 times 5. That's a sad looking 2. The square root of 25 is 5, so I get 5 square roots of 5. And finally, the square root of 80 would be the square root of 16 times 5, which is 4 square roots of 5. So in this case, they all simplified. 2 plus 5 is 7, minus 4 is 3 square roots of 5. Anyway, with that, I'm going to stop the